the center of mass, but it's the same concept. So does anyone have a question from the homework or the quiz or the worksheet or anything before we start doing review stuff, formal review stuff? Anything jump out at you as problematic? So let's do these last two examples then of the center of mass ones. Make sure we're all following. So the two formulas, oh, that thing's busted. The two formulas, again, are given to you. And notice when we look at the x bar formula, the x bar formula is for m sub y. So the y-axis, if we think about the y-axis is here, x bar is measuring from the y-axis. M sub y is the moment about the y-axis. It's a tendency to rotate about the y-axis. So that's why it's got an x bar and an x here, because this x is measuring the distance from the y-axis. So there's no typo there. Sometimes it feels like, oh, well, if that's x and that's x, why is that y? But that's what's happening. All right, so m sub y, you're rotating about the y-axis, and x is measuring that distance away from the y-axis. So when you're looking at these, the nice thing for a centroid is that the rho, the density is constant, and it just cancels out. There's a density in this, and there's a density in that, and they just cancel. So we end up with just 1 over area. And this should look like the area integral other than the x. So it's just area, upper minus lower, multiplied by x. And then the y bar is used for the moment about the x-axis. So y bar is measuring distance from the x-axis. So that's going to be an m sub x, and same idea, the rows cancel, and we just end up with a 1 over area. And then remember that this x is the distance to the y-axis. The distance to the x-axis we saw was f plus g divided by 2. That's the distance to x-axis. And so this integrand comes around by taking f minus g and then multiplying it by f plus g, which gives you a difference of squares, and then you have the division by 2. So f squared minus g squared divided by 2 is going to give us our y bar. But it comes that the concept is the same. We're multiplying by the distance to the y-axis, and this one we're multiplying the distance to the x-axis. So let's just take a look at two more examples. So we've got that region right there. We want the center of mass. We've identified the upper curve. We've identified the lower curve. And so the first thing we do is just find the area. So when you're in physics and you don't have uniform density, you have to find the mass, and that's going to be a lot more complicated. But for us, where we're just doing center of mass of a uniform lamina with uniform density, we don't have to deal with finding true mass. So area, upper minus lower, and we get that value right there. And then x bar, we do 1 over the area, so 1 over that. And then it's the same exact integral that we had for area, where we have upper minus lower, and the big difference is that we just multiply by x. Go through the integral, and we get that. There's our x bar. So it's not super complicated. You're going to be given the formulas. But as you're working the formulas, you want to try to think about these concepts a little bit and try to get used to thinking about, okay, that's distance to the y-axis. And then for y bar, we do f squared minus g squared divided by 2. F squared minus g squared divided by 2. Same limits of integration. So everything just sort of, you've got the same structure. Same limits of integration. It's always dx. Nothing real weird that you have to think about. And once again, you sort of grind through. Usually the integration itself is not too hard. There's our y bar, so that's the center of mass, or the centroid. 1/2, comma, 8/5. So there's 1, so 1, so somewhere right there. So if that thing were laying flat, and you stuck your pencil right on that center of mass, or that centroid, the thing would balance on your pencil. Okay, so one more of these. So notice with this one, once again, we identify our upper curve, we identify our lower curve. And to find area, what we've been doing is integrating upper minus lower, but this is a geometric shape that we have a geometric formula for. So we could just do the area of a semicircle. So area of a circle divided by 2. So we could shortcut this one. Now to get to x bar, all right, we have the upper, that's the upper, minus the lower. Lower is 0. So it's gone. And then we have this distance to the y-axis. All right, so this is just the regular x bar formula. And we get 0. Of course, right? You look at that shape, and we have symmetry about the y-axis, which tells us x bar's got to be right on the y-axis. Right, so we can see that through symmetry that x bar's got to be 0. Again, because we have uniform density. If the density weren't uniform, of course, that would be not necessarily true. But because we have uniform density, we are just looking at the geometric center. So x bar has to be 0. And then when we go to find y bar, same idea. We're doing f, the upper curve squared, minus the lower curve squared. So f squared minus g squared, and then divide by 2. And that one is not 0. That one ends up being 8 divided by 3 pi. So that is our center mass, or our centroid. So there are, you've done problems 1 and 2 on Thursday last week. If you could practice those again. So these are the 4 practice questions that you want to make sure you can do. And if you want to do more, I think I have the link right here. So Paul Sieberger's got some other ones there that you could also work. He has them set up on his website where he doesn't show you the answers. You can work through them and then reveal the answers if you want to do more than those 4. Those 4 should be enough, though, because you're given the equations. There should be enough to get you going on that one center of mass question that will be on the test. Any questions about center of mass before we start our review? All right, well, so again, the prior exams are here. So the 2 prior exams, the last 2 exams, right there. So take a look at those. Let's go to the review for 8 and 9. And this just sort of, the first slide is just an overview of everything we've done this section. No calculators with an integral button for the test, no phones, no note cards. So we've got all these questions, which are also in MyMathLab. If you want to do it through the MyMathLab's quiz feature, you can also work on these problems through there. So we've got all these questions. And last semester, I put a video for all of them to solve them, just in case we don't get to them. So any ones we don't get to today, you can look and see the solution. So first one, just kind of a basic reverse chain rule. We could use substitution. Hopefully by now when you look at this, you aren't inclined to use substitution, hopefully. And remember that your markers, you're looking here, if you were going to use substitution, you're going to let u be generally what's in the parentheses. It's either the base of an exponential expression, it's what's inside of an angle, it's what's inside of a square root, sometimes it's what's inside of a denominator. It's usually pretty obvious what you want to let u be. And what we notice here about u if we were to do the regular u substitution, is that, oh, the u is linear. And so we've got a shortcut whenever we have a linear substitution, which we have been calling RCR. So we call this in this class reverse chain rule. So instead of multiplying by the derivative of what's in the parentheses, which you would do if you were taking a derivative, you would be doing chain rule. But we're integrating, so we're doing reverse chain rule. So instead of multiplying, we're going to divide. So we are going to take the base, 2x minus 1. We add 1 to the exponent. Negative 4 plus 1 is negative 3. We divide by the new exponent. But we also have to divide by the derivative of the inside here. So we're also going to divide by that too. And then we have a plus c for the integration constant. And if we wanted to simplify this, we'd probably put the negative out in front. And you could do this in a number of ways. Usually, we like to write it without negative exponents. So that would be our simplified answer. So reverse chain rule. And so in 8.1, we had this sort of litany of different special cases, which can be hard when you're integrating, when you have a different technique. There she is. She's close. She's so close. There. She made it. All right. She's healthy.
She's never going to walk in late.
Sorry it was late. There
Right?
was construction traffic.
Oh, was there? What do they do in construction?
By baseline. Well, everywhere, but yeah, by baseline.
Construction everywhere. Okay, so this is one of those one-offs where we see negative exponents. And the negative exponent thing, our strategy was to get rid of the negative exponents. So we have to be clever on what we multiply by. We want to use our fairy dust. We want to multiply by 1. Multiplying by 1 is a very common strategy for us. And here we want to multiply by a version of 1 that's going to make those negative exponents go away. Well, there's only one negative exponent, so we want that one negative exponent to go away. And so generally, it's not too crazy. We generally are just taking whatever that factor is and changing the exponent from negative to positive. But if we multiply the bottom by that, we have to multiply the top by that. So we have to do that balancing act. And then we rewrite our integrand based on that multiplication. So e to the 4x times e to the 4x is e to the 8x. We add exponents when multiplying exponentials with the same base. Down below, we have to distribute. So that this term has to be multiplied by each of those terms. Have to distribute. So e to the 4x times e to the 4x is e to the 8x on the left side. And then we have our minus sign. And then here, e to the minus 4x times e to the positive 4x is e to the 0, which is 1. So we're left with just that 3 right there. It is an equal sign, not an approximation sign. And now we have another decision to make. What would be a good strategy at this moment?
U sub.
So we could use u sub with u being the denominator. But there's a shorter way.
Can you make it a log form?
Log form. If we think about the denominator's derivative would be e to the 8x times 8. Right, derivative of negative 3 is 0. U substitution will work just fine if you let u be the denominator. It's going to work out just fine. But if we notice, this log form option, we can sprinkle the fairy dust again, we can throw a 1 in there in the form of 8 over 8. And now the denominator's derivative is exactly the numerator. And so now it's in what we have been calling log form. So log form, and I'll put a little LF here just as a reminder that it's log form. So 1/8 natural log, absolute value of the denominator. So there is our antiderivative. So we've had a few techniques already. We've had reverse chain rule, so keep that in mind, reverse chain rule. We had negative exponents, get rid of negative exponents by multiplying by something that's going to cause a 0 in the exponent position. And then log form. So those are all 3 little kind of one-off different things that we will encounter. And then this was another one of those one-offs. We have a quadratic in this denominator that's not factorable. If it was factorable, what would be our strategy? Partial fraction decomp. If you can factor the denominator, then you go to the A, B, the PFD, partial fraction decomposition. If you can factor it. This quadratic we can't factor though, so we don't want to go to PFD, but we do want to complete the square. So in the denominator, when we look at that middle term, the coefficient is 2 or negative 2. It doesn't matter because you're going to square. So whether you think of taking negative 2 and dividing by 2 and squaring, or taking 2, dividing by 2 and squaring, it doesn't matter because it's going to be positive no matter what. So the missing constant that we need, or the constant that we need to allow the completion of the square, so we're looking just at these 2 terms right there. We divide that by 2 and square it, we need a 1. 2 divided by 2 is 1, 1 squared is 1. So we're just going to borrow that 1 from this 50. We're going to rewrite the 50 as 49, and we're going to group the 1 over here. So now we have a factorable perfect square trinomial. So that is perfect square. And let's rewrite it, factored. So this will be x minus 1 quantity squared plus 49. So the way we've been doing these in class, we see that sum of squares. And as soon as we see that sum of squares, we're thinking trig substitution, or maybe it's an inverse trig function right off the bat. We've seen that inverse sine and inverse tangent. There's sums and differences of squares right in those initially. So we might be able to do it immediately without trig sub. But we have been doing it in class where we create that difference or sum of squares with a 1. So if we can create a sum or difference of squares with a 1, that sort of brings it down to the base case, the simplest case, where we don't have to deal with the a. So if we rewrite this, the 49, we look over here and there's no 49, so you just create one. You conjure up a 49 so that it can be factored out to the front in the denominator. And then the stuff that's left here, we want to write it as a single square. So that's x minus 1 over 7 quantity squared plus 1. Now we've written it in the arctangent form, the basic arctangent form where we've got that constant being a 1. And so right here, we can immediately go to the answer. So we can write this as 1/49. I'm going to leave a little gap for the RCR, for the reverse chain rule. And then this is arctangent of whatever's in parentheses. So x minus 1 over 7 plus c. And now in our little reverse chain rule slot right here, we need to fill in whatever we need to do the RCR piece. And what's going to go in right there? What's going to go in our RCR slot?
1/7.
So the derivative of that parenthetical quantity is 1/7. We divide by 1/7, which means we'll multiply by 7. So we'll put a 7 over 1 in here. So this is the RCR right there. And that's because if we come over here and just make a note, x minus 1 divided by 7, that's 1/7 x minus 1/7. So if you took its derivative, you would get 1/7. The coefficient of x is the derivative. And if we divide by 1/7, that gives us our 7 divided by 1. So there is our RCR. A little bit of cancellation out in front is all we have to do. So we get 1/7 the arctangent of x minus 1 divided by 7 plus c. So that is our antiderivative. Now, if you, yeah, Luke,
Zach,
I know.
why for this one do we not have to do the whole like u equals the inside and draw a triangle and stuff?
Because this is a direct application of this integral right here. We were in this form. This integrates directly to arctan.
So there's nothing on the top. Okay.
There's no, so if this had big parentheses and a half or 3/2
Or that, sure.
yeah, something more complicated. Now, if we didn't see that right away, if we saw, ooh, sum of squares, trig sub, it's a tangent, let's do it. So this, so let's just say or over here. Or we could say, let's use trig sub, and we would choose tangent because it's the sum of squares. So sum of squares, t, always tangent. If we differentiate both sides here, we get 1/7 dx equals secant squared of theta d theta. And then our integral is going to become, there's a 1/49th in front. And then the numerator is a dx. And that dx needs to be replaced with theta. So we come down here and we say, oh, the numerator, dx, we multiply both sides by 7. We would have 7 secant squared of theta d theta. So that's the dx. And then in the denominator, we would have tan squared plus 1. And what is tangent squared plus 1? Secant squared, right? Tan squared plus 1 is secant squared. That's our classic Pythagorean identity. We extend here, come down. This side is tangent theta. This hypotenuse is secant of theta. And that distance across there is 1 because we're on a unit circle. So 1 plus tan squared is secant squared, Pythagorean theorem. So that means that this secant squared right there is going to cancel with this entire denominator, which becomes the secant squared. So we're left with 1/7 integral of d theta. When you integrate d theta, you get theta. But theta is equal to, if we come up to our initial substitution, that theta is equal to the inverse tangent of the other side there. So x minus 1/7 plus c, which of course is the same answer. So if you don't see that you have the basic setup for whatever it is, whatever the arc function is, you will always end up with this integral of d theta, and it will come out anyway. You know, sort of the easiest type of trig sub. You end up with just an integral of d theta. So, yeah, it works out fine either way. It's the quickest type of trig sub that there is if you don't really need it. It's the quickest one. But, so if you get good with that trig sub, you don't even really need to remember those 3 inverse trig integrals anymore, because all you have to do is remember that if it's plus, you use tangent, and it's going to come out in the wash anyway. So that's kind of nice. All right. ultraviolet voodoo. We have a product. And this is sort of the classic case for ultraviolet voodoo when you have a product of functions. So right there, we see two functions. And ultraviolet voodoo, integration by parts, we are going to break apart the integrand into a u and a dv. And that's going to create that, our table there. Let's put it down here. So we're going to have a u and a dv. So the integrand needs to be broken apart into these two pieces. So the x and the e to the 4x can go in either one of these. Now the rule of thumb that I generally emphasize is that we want to pick the most complicated chunk that we can integrate easily and put it with the dv. And so of those two functions, e to the 4x is more complicated than x. And so that would be the natural choice, in my opinion. That would be the natural choice. Now another rule of thumb is that if one of your factors is a power of x, putting it with the u is nice because then you're differentiating it and that's pulling the power down. Right? So if you have x to the 3 and you took its derivative, it would be 3x squared. So the power is going to be decreasing. So it's another good rule of thumb to think about. If there's a power of x, putting it with u is kind of nice because it's going to reduce the power. We had one exception to that, and that was when we had a natural log inside. And so when you have a natural log inside, what we saw worked most often was actually putting the log over here. The derivative of natural log puts an x in the denominator, so it has the same effect that the power will go down because you're going to divide by x. But in general, power of x going here is a good idea. So we differentiate both sides here, and we get du is equal to dx. We integrate here. And this is a good example of why reverse chain rule, hopefully by now, is second nature. You don't want to have to use u substitution just to get from here to here, ideally. And so we do our reverse chain rule. The integral of an exponential is itself. And then you divide by the derivative of the exponent, if the exponent is linear. And that is linear. So now we're ready for the ultraviolet voodoo. So this is going to be UV, ultraviolet, main diagonal. So 1/4 is the constant, and then an x and an e to the 4x. Can be written in different ways. So there's UV minus the integral of voodoo. So voodoo is down below, v to u. There's our voodoo, it's the bottom row. And so that's going to be 1/4 e to the 4x dx. And here is where we come to our checkpoint. This integral is easier than the prior integral, so we're doing good. We're on the right track. If that integral is more complicated, if it became an x squared times e to the 4x, if it became more complicated, we know we're on the wrong track. And then we would switch these two functions. If it's the same difficulty, then we're probably in one of those integration by parts with a twist problems, if it's the exact same difficulty. But this one, it's getting easier, so we're golden. So we have that. The integral of this, we just need to do a reverse chain rule, so we're going to get minus 1/16 e to the 4x plus c. And I'm sure you've probably noticed this pattern where your terms, often you see this decreasing of the power of x term by term as you're moving through. And that is our answer. Don't forget your plus c. No need losing points for not putting the plus c. So that is that's probably pretty routine integration by parts. Nothing too weird there. So let's do one with a twist. Once again, we have a product here. So this product is often integrated with integration by parts. That's kind of one of the classic types of integrals that we can do with integration by parts, the integral of a product. Now, this one is going to be one with a twist. And the way we can sort of have a heads up that, oh gosh, this is going to be a twist is because both of these functions have that circular nature to their derivatives. Derivative of an e to the x is an e to the x. It keeps on going. Derivative of cosine is sine, and the derivative of that is cosine, so that's looping through also. So if you have two functions that have that circular nature to their derivatives, you're going to get the twist thing. So with these, we generally find it easiest to call the integral something. We'll use omega. We'll use omega. You can use whatever your favorite Greek letter is, whatever letter you want. And it's not going to matter. When you do your UDV, it won't matter with all of these twist type problems what you pick for U and what you pick for DV. It's not going to matter. So generally, you want to pick what works best for you. If it's easier to integrate the e to the x, then put the e to the x over there. If it doesn't matter, just leave it in the same order. I usually just put it in the same order. Integrating cosine should not be hard by now. Should be easy by now. So the left column here, we do derivative. We have to use the chain rule. Don't forget the chain rule. Chain rule, we multiply by the derivative of the exponent. And then over here, we use reverse chain rule. We integrate the outside function and get sine of the same angle. So that's the integral of the outside function. The outside function is cosine. The inside function is 2x. We divide by the derivative of the inside function. So that is going to be our integration by parts table. Our voodoo ingredients. So this tells us that our integral is going to be uv, which is this main diagonal right down here. There's our uv. So that's going to be a 1/2 is the constant, and then usually we put the exponential function in front of the trig function. So uv minus the integral of v to u. So v to u is the bottom row, the voodoo part. So uv minus the integral of v to u. So I'm going to put the constant together. It looks like a 3 in the numerator, a 2 in the denominator, so I'll call that 3/2. And then the exponential, e to the 3x, and then the trig, sine 2x, and then a dx. All right. So this is one of those places where we look, we check, at least make a mental check that, okay, is this new integral easier, harder, or the same difficulty? We see it's the same difficulty. That reinforces that we're doing the twist. Same difficulty, we have an exponential times sine. So we have to use integration by parts the second time. When we use integration by parts the second time, we want to be consistent. Whichever type of function we use for u, we want to keep doing that. Now here's where we can be a little clever. This minus sign is a pain. Right? The integral piece is going to turn into a uv minus integral of v to u. And if there's a minus in front of all that, you have to have big brackets, and the minus is going to have to distribute. If you have some foresight, you can turn that into a plus and just shove the minus on the inside, and then you don't have to worry about huge brackets with a distributed minus sign. Does it matter? No. But it makes it a little cleaner to not have to have the big brackets with the minus sign. And somebody asked this in the course of when we were doing this earlier. this minus 3/2, when we look at our original, we're sort of thinking of the exponential function as one function and the trig function as the other function. You could put the minus 3/2 with either one. It doesn't matter. You could let u be e to the 3x and dv be negative 3/2 sine 2x. It doesn't matter where you put the constant. It's not going to matter. I'll just leave it in the order it's there for simplicity. So I'll put minus 3/2 e to the 3x here and sine of 2x. And don't forget that the differential has to be here, right? That dx is part of the integrand. It comes with the dv. It has to be with the dv so that you can integrate both sides. So you've got the v and the x separated. So in our derivative column, derivative of an exponential is itself multiplied by the derivative of the exponent. And that should have a dx in it also. And then our integral column, we use reverse chain rule. So the outer function is sine. Its antiderivative is minus cosine. Inner function's derivative is 2. We divide by the 2. Okay, so we are, let's maybe, actually, I might just move all this stuff over here just to keep it a little cleaner. Put you over there. Okay. So then we're going to just replace this second integral with the uv minus integral of v du stuff. All right. So this first function's coming down, and then we have plus uv down here. So our uv, we multiply this diagonal. So the constant part is negative 3/2 times negative 1/2. So that's going to be positive 3/4. And then the exponential part is e to the 3x. The trig part is cosine 2x. Everyone okay with that? So that's the uv. Minus the integral, bottom row, the voodoo. So there's the voodoo part. So minus the integral of the product here, the constant part, negative 9/2, negative 1/2, that's positive 9/4. And then e to the 3x cosine. So does that make sense to everybody? And everyone okay with the voodoo part? And so the nice thing about putting that minus sign up in here is that it just got a lot cleaner here. We didn't have to worry about distribution. You know, it just simplifies our life a little bit. So now this is where we notice that on the right-hand side, this is just minus 9/4 times capital omega. That is what we let omega be. Oh boy, where are you? Oh, there, okay. So we said that omega is equal to the integral of e to the 3x cosine 2x. So e to the 3x cosine 2x, that part's omega, and then we just have this coefficient of negative 9/4 in front of it. Now we're back to algebra 1. On the left side, we can put these in if we want. Right, there's an omega there, and we can write it, we can think of it or write it as 4/4. So we have 4 omega over 4, we have 9 omega over 4, and we add them together. So we will get, when we add them, we'll get 13 over 4 times omega equals all this stuff on the other side. Now, the one thing we have to be cautious of is we need to, as soon as we move those omegas to the left side, we have to put a plus c. Because we're dealing, omega is an indefinite integral, right? Omega is this indefinite integral. We know indefinite integrals are going to have a plus c. So when we do this little twist, when we twist that over, we have to remember that there's going to be a plus c as the arbitrary constant on the right. And what is our final step here then?
Multiply it by 13.
Multiply by the reciprocal. Divide by 13/4 or multiply by 4/13. Right? Yeah. Good. Thanks. So multiply by 4/13 because 4/13 times 13/4 is 1. So multiply by the reciprocal. So 4/13 is coming over here. So we're going to have 2/13 e to the 3x sine of 2x. 4/13 here, the 4's will cancel, so we get 3/13. And that is our final answer.
I have a really stupid question.
Excellent,
From the very
Landon.
beginning.
Back to the very beginning?
Yeah, roughly from the
Sure.
beginning. When we do the first ultraviolet, would you be able to hold the -3/2 just in front of the integral?
100%.
Okay.
So if you wanted to pull the -3/2 in front, when you do the second integration by parts, you would have big brackets around the whole integration by parts thing, and you would have a -3/2 out in front.
Okay.
And then that -3/2 would have to jump across and distribute. So the whole point of pulling that negative inside, leaving the constant on the inside, is that you don't have to deal with the big brackets and the distribution.
Okay.
But absolutely, if you're careful and you put the big brackets and you factor out the -3/2, it will be the same. Just a little bit more algebra.
Would you allow tabular integration on the exam?
Sure. Yeah, if you've looked up tabular integration, you've played with it, it reduces the work a little bit. There's a slight twist when you're doing integration by parts with a twist to tabular integration, but yeah, you could do it for sure. For sure. Any other questions on the voodoo? Okay. Voodoo it is. Oh, geometry now. Okay, so I see an exponential function here. Question. Does an exponential function's graph go through the origin? No! No, no, no. Exponential function does not go through the origin because if you plug in 0 here, what do you get? 1. Yes. Okay. Right? If you're not 100% sure on your graph, plug in a couple of values. Right? It's not about memorizing, it's about deduction. And it's like, okay, you know an exponential growth function is going to be going up to the right. You know an exponential decay function is going to be going down to the right. And so we know that this is an exponential decay because of the negative. And it's not going to cross the x-axis. It's going to do something like that. It's going to approach it real fast. Okay, so there is our f. And then it tells us that we want to go from 0 over to natural log of 6. Who knows what natural log of 6 is? Doesn't really matter. We just know that it's to the right of 0. So then we have this region right here that we are looking at. And they tell us, find the volume of the solid generated when the region bounded by exponential decay and the x-axis on this interval is revolved around the line x equals natural log of 6. So now we have our axis of rotation. will that turn into a line? Okay. That is our axis of rotation, right there. Going around that line. So we're going to create this little bowl-looking thing. We want to find the volume of that bowl-looking thing. So when we look at this region, is this region vertically simple or horizontally simple? So if you start drawing vertical elements and horizontal elements, which way is it more simple to draw? Vertical elements or horizontal? Vertical, right? Hands down, no matter where you draw your vertical element, you have the same upper curve and the same lower curve, no matter what. So that means it's vertically simple, right? You can draw that vertical element anywhere, you don't get any ambiguity. Whereas horizontally, it is not horizontally simple because there you've got the right curve being the line, x equals natural log of 6, but up here, the right curve is the exponential. So you do not have a consistent right curve. So it is not horizontally simple, so we definitely are drawing a vertical element at a random x. So now we imagine that vertical element right there, or that rectangle, however you want to think about it, and we have our axis of rotation. When they're parallel, that's when you create a cylinder, right? Perpendicular, you would create a washer if there's a gap, and a disk if there's no gap. So this is going to create a shell, or a cylinder. And so then we find the area of our cylinder or shell. First, generic area, 2 pi RH. Cylinder, 2 pi r is the circumference of the base. Multiply it by the h, and you get the area of the cylinder. Hey, you have a question or good? So 2 pi RH, area of a cylinder. So if you're trying to visualize this representative cylinder, you're sort of thinking about, it's where I drew that element, we have, sort of, looks sort of like that, right? That's going to be the cylinder-ish. Maybe I drew that a little too far to the right. So it should be symmetric right around that line. So it's going to look sort of like that. Okay. We need to use dx or dy. If you chose a vertical element, the thickness of that is dx. That tells you use dx. If you draw a horizontal integration element, a horizontal rectangle, the thickness of that is dy. You'd have to use dy. But we chose a vertical integration element, a vertical rectangle. Its thickness is dx, so we know we're integrating with dx. That tells us that this r and this h need to be turned or converted into x's so that they match the dx. So when we look at our picture here, our vertical element is right over here. Let's look at the distance it is to the axis of rotation. That is r. Right? That's the radius of the cylinder. The height of the cylinder is right here. Right? That is going to be the height of the cylinder. All right, so that should allow us to convert these two. So what is the radius? So before you say anything, think horizontal. Horizontal distances are right minus left. So that horizontal distance, that radius, has to be the right x value minus the left x value. All right, so what is the right x value for that horizontal segment? ln6, that's the right x-coordinate. And the left x-coordinate is x. That's what we called x right there. So that purple distance is the distance between these two x coordinates, one that we called x and one that we called natural log of 6. Horizontal distance is always right minus left. So that's going to be ln of 6 minus x. That's the radius. And then the height,
The function.
The function.
Negative x.
right? That's what the function is. The red function, e to the negative x, that is measuring the distance from the x-axis up to the red curve. Right? That's what e to the negative x is measuring. So the height is going to be e to the negative x. Any question on any of those pieces? All right. How do we get to volume? So we integrate area to get volume, just like we integrate length to get area. We've got that bootstrapping thing. So the volume, 2 pi can factor out to the front. So here's one of these cases. Let's pull the 2 pi out to the front, and we'll see how we have to deal with big brackets. If we didn't want to deal with big brackets, we could leave the 2 pi in. This will be an example where we can see how that would work. So our integral limits are 0 and natural log of 6. And then we're going to integrate, and I'll distribute right away that e to the negative x thing. So we have that. We're going to break this into 2 integrals. So we're going to have 2 pi multiplied by this first integral. First integral has a natural log of 6 that can pop to the front. Okay, so we have that integral, and then minus, all right, this integral is also 0 to natural log of 6, x e to the negative x dx. Okay, so this time we're going to have the brackets with the 2 pi, and I'm going to leave the minus on the outside just so we can sort of see an example where we're not going to try to think ahead and avoid the big brackets thing. So the first integral, no problem, right? It's got a linear exponent, it's an exponential, it's just reverse chain rule. So e to the negative x divided by negative 1. That's the RCR. That gets evaluated on the interval 0 to natural log of 6. Now, here we have a product. We've got the whole product in here, so we're going to do the integration by parts of the, just integration by parts. So we have the u, we're going to do the voodoo thing. We have the power of x as one of our 2 functions. And we have an exponential as our other function. If we just think for a moment, if we use that general principle, put the more complicated thing over with the dv, then it will work out just fine. So e to the negative x is certainly more complicated than x. But the other idea to think about is that putting the x with the du, or with the u, is going to cause the power of x to go down when we find du. So du will be dx. Ooh. Du will be dx. So d, and then v will be negative e to the negative x. So in here, we've got the minus sign, remember, so now we have to have more brackets. That minus sign has to distribute across the ultraviolet voodoo from this. So this is going to be negative x e to the negative x. That's the main diagonal. Main diagonal is top left to bottom right. So uv minus the integral of v du. Okay. Then that bracket, and then 0 to natural log of 6. And then in here, we also have a 0 to natural log of 6. We have all that. So a lot of brackets when you pull the constants out with integration by parts. Now, all of these evaluations are on the same interval, 0 to natural log of 6. It's generally easiest just to wait to the very end and evaluate the whole antiderivative once you establish it, instead of doing it in little pieces. So we're just going to pause, not do it yet. So we've got our big bracket here. This is going to be minus natural log of 6 multiplied by e to the negative x. Minus gets distributed here to make that positive x e to the negative x. Okay. Now we have a bunch of minuses happening here. This minus times this minus right in here, you can imagine that as becoming a plus, but then this minus here is coming across. So we're going to have 3 minuses that are going to combine into a negative. All right? There's 3 minuses here. 1, 2, 3 when we come to distribute it to this second part. Now we do the integration, and we get the integral of e to the negative x is e to the negative x divided by negative 1. So we have a 4th minus, which then makes that positive. So this minus up here is coming into play with the reverse chain rule piece. And now we've done the integral. We've got all the stuff. I guess we could have used parentheses instead of brackets. So there is our big ol' antiderivative. Let's plug in the upper limit of integration. So we have, let's see. Let's come off to the side just to make sure it's clear, because we have a bunch of e to the negative x's. So if we do e to the negative natural log of 6, there's a few ways you can think about this. You can pull that negative into the exponent position inside the natural log. The e and the natural log are inverses, so those cancel. They annihilate each other, and you end up with 6 to the negative 1, which is 1/6. So e to the negative x evaluated, so all of these evaluated at natural log of 6, they're all going to become 1/6. Is that okay? So those all become 1/6. So here we're going to end up with minus natural log of 6 over 6 plus, this is going to be 1/6 times natural log of 6. So natural log of 6 over 6 plus 1/6. So that is this entire antiderivative evaluated at ln 6. And now we subtract off the entire antiderivative evaluated at 0. And here we have to be careful also because we're subtracting off the entire thing. So maybe let's leave that in parentheses to evaluate each of these at 0. Well, e to the 0 is 1. So we're going to have minus natural log of 6 times 1. Here, we're plugging in 0. So we're going to have 0 multiplied by 1, which is 0. And then here, we have a 1. We'll have all that. So these two cancel each other out. And what are we left with? So we have 2 pi on the outside. We have a 1/6. Distribute this minus. We have plus natural log of 6. And then minus 1. The only thing we can do is combine the 1/6 and the 1. The 1 is minus 6 over 6, so we're going to end up with minus 5 over 6 plus natural log of 6. Whew. It's a doozy. Can't even remember what the original question was. Was this the one that we were finding volume on?
Yeah, this was the volume of that.
This was the volume of that? That feels like it was so long ago. All right, volume of that ashtray looking thing. Yeah. Wait, do they still have ashtrays? All right, let's take a break. 10-minute break. Clear your mind. Go outside where it's like 100 degrees in March.
Back and a 1993 Las Panopera. It's just like a SUV.
Every single like laser rooms. Do you want to build roller coasters?
Yes.
We could use a laser.
So our next topic, integrating products of powers of sine and cosine. And when we look here, we see that we've got this sine factor, we've got this cosine factor, and we had a rule that said if one of the powers is odd, pull one off and convert the leftovers. The power on cosine here is odd, so we're going to pull one off and convert the leftovers. The 4 can come out to the front. We're going to leave sine to the negative 3/2 alone. And we'll do it in stages here. So we're pulling off one cosine, and we're going to group that with the differential. So we're sort of thinking of this as blocked off. We're pulling off one factor of cosine. These ones are the ones that I will refer to as the leftovers, right? They were left behind. And those need to be converted into what function? Sine. Right? We're pulling off the cosine with the strategy that if we let u be sine, the derivative of sine will then grab that cosine of x dx. So the leftovers need to be converted into the co-function. So we'll have 4 integral sine to the negative 3/2 x cosine squared is 1 minus sine squared. And then we have this cosine x dx, which we're thinking of as waiting for u substitution. So we'll let u be sine. And then du is cosine of x dx. And so with these products of powers, you get rid of the trig functions really fast. It's just, one step to rewrite it, and then you do your u substitution, and the trig functions are gone. So this will become 4 integral u to the negative 3/2 1 minus u squared du. Now, if you're a glutton for punishment, you could say, hey, there's a product there. Let's do integration by parts. Hopefully, you see that, yeah, you could do that, but it's a little easier if you just distribute and use the power rule. We can distribute that and use the power rule. That's going to be a lot easier. So the power rule is going to give us, we add 1 to negative 3/2 and get negative 1/2. So u to the negative 1/2 dividing by negative 1/2 is the same thing as multiplying by negative 2. And then we add 1 and get u to the 3/2. Dividing by 3/2 is multiplying by 2/3. And then we have plus c. And now we just have to replace u with what we let it be. We let u be sine. So, and I'm going to distribute the 4 at the same time. Right now the 4 is only factored out of 2 terms. We've got 3 terms including the c. There's no point in factoring if you're not factoring out of everything. So this is going to be minus 8. And then u to the 1/2, that puts a u to the 1/2 in the denominator. So we'll make that square root of sine. And sine of x, not theta. And then minus 8/3 sine raised to the 3/2 power of x, and then plus c. Do I have that? And if you were so inclined, you could move the sine into the numerator and make it the square root of cosecant. If you wanted to have no trig functions in the denominator, doesn't matter to me. Any part of that you have questions on? Not too bad? Okay. Let's see, what time do we have? We're doing pretty well. We want to make sure we get to the impropers. Let's do, let's see, that one, that one. Let's do this one of the tan and secants. So when we have tans and secants, our two strategies are regarding the power on secant being even or the power on tangent being odd. And both of those are candidates here, right? We could go either way because secant has an even and tangent has an odd. So this is kind of like the one that was on the worksheet where it said which is the more, which way is going to be easiest. And when we're looking at this, the way that's going to be easiest is the way that we have to do the least conversion. Like converting to the other trig function can be a pain in the neck. And so if we think about this, if we go with the tangent thing, tangent's odd, we'd pull one tangent off with the secant, we pull off a sectan, and we'd have to convert tangent to the fourth. So that's tangent squared squared. So that's going to be secant squared minus 1, quantity squared, which will then be FOILed out and be a big long fourth order thing. If we look at secant squared, if we pop a secant squared off, we're left with secant squared, so we only have to convert a secant squared versus a tangent to the fourth. It's easier to convert a lower power. So it makes more sense to peel the secant squared off. So we can pull the 7 out, leave the tangent to the fifth alone, pull off a secant squared. So this secant squared that we pull off, this is going to be grouped with the differential. We're going to leave it there for the u sub, with the idea that if we let u be tangent, tangent's derivative is secant squared, and that's going to grab that pink box. So the leftovers are right here, and these leftovers can be converted very easily. Why is it not wanting me to? So these are the leftovers. So we'll convert those with that identity right there. So tangent to the fifth of x, secant squared is the hypotenuse. That's tan squared plus 1. And now we're ready for sub. Let u be tangent, everything turns into u's. We have powers of u, which are pretty easy to manage. So u is tangent meaning du will be secant squared of x times dx. So we've got that. So again, you see a product there, so if you're a masochist, you could say, I'm doing integration by parts. I wouldn't recommend doing that. It's going to be a little easier, bless you, if you just distribute and use the power rule. To each his own. So we'll distribute that. And then we're going to use the power rule. So power rule is going to be pretty easy here. We're going to get u to the 8 over 8, u to the 6 over 6, plus c. So then we're going to back substitute. We let u be tangent, so the u is going to be substituted by tangent. And we'll distribute that constant. Once again, it makes no sense to factor something out of just part of your expression. Question?
Does it matter what order we have them in?
No.
Or, okay.
No, yeah. Descending order, increasing order, mixed up like alphabet soup, doesn't matter. Yeah. All good. All right, let's skip the next thing. Let's get to trig sub. That's more complicated. All right, trig sub, difference of squares. Difference of squares, we want to use sine, secant, or tangent. For a difference of squares with a leading one. What was that? Sine, secant, or tangent? Not tangent. That's a great start. Not tangent. Not tangent. So then we have to ask ourselves, is it 1 minus sine squared that's an identity, or 1 minus secant squared that's an identity? 1 minus sine squared is cosine squared. Right? If you look here, if you tried to do 1 minus secant squared, you'd end up with negative tangent squared, which is bad. Because you're going to be taking a square root, negative, you can't take the square root of a negative. But 1 minus sine squared is cosine squared. And if you're a contrarian, you could use cosine instead. But usually we use sine, secant, or tangent. So we'll use sine in the long run here. But I do want unity. I want a 1 here. I want a difference of squares with unity, with a 1 right there. So we're going to factor out the 196. And that 196, when it factors out, it's got to come with that power that's on it, that square root. So this is going to be square root of 196 right there. And once again, there is no 196 with this x squared, but we can create one. We can put a 196 over 196. The 196 that's factoring out is right there. And what is the square root of 196? 14, exactly. Let's see. So this is going to become 1 minus x divided by 14 quantity squared, dx on the outside. So here is where we're going to pick the sine, secant, or tangent. We've got a difference of squares with the leading 1. So we're going to let x over 14 be sine. And so this would give us, when we take the derivative, 1/14 dx will be cosine of theta d theta. that's going to become 1/14, bless you. All right, so now we have some work to do. X squared, we look down here, we're going to multiply both sides by 14 and then square both sides to get x squared. So x squared is going to be 196 sine squared. 196 sine squared of theta. And then we look at the dx. Dx, we come down here, multiply both sides by 14. That's going to be 14 cosine theta multiplied by d theta. And in the denominator, we have the root of 1 minus sine squared. So that is our full substitution. Do not be sloppy. Make sure you have this dx written down because that's a big chunk of that. Do not forget your dx's. Okay, there is some cancellation here. That 14 and that 14 can go away. Is it clear, or should I write in this intermediate step? 1 minus sine squared is cosine squared. Square root of cosine squared is cosine. So this whole piece right here turns into cosine, which is going to take away that cosine. Everybody okay with that? 1 minus sine squared is cosine squared. Square root of cosine squared is cosine. Cosine cancels with cosine. So we end up with 196 integral sine squared of theta d theta. What do we do when we have an even power on sine? Power reduction. So even power, we have to power reduce it. So that's 1/2. There's a 1 and a cosine of 2 theta. Is it plus or is it minus? Minus. Sin is bad. Sin is negative. Whatever it takes to remember it. So then we have 98 out in front. And if you integrate 1, you get theta. If you integrate cosine, you get sine of the same angle. But then you have to reverse chain rule it. So we've got that. And then we need to use our double angle identity for sine. Sine is 2 times sine of theta times cosine of theta over 2. And those 2's will cancel. Now, we get to create our magic triangle. So we have a right triangle. We always draw it as if it's in quadrant 1, and we put theta right there. And we build this triangle based on this expression right there. All right, that equation right there. X over 14 is sine of theta. So sine of theta is opposite over hypotenuse. Sine of theta, x over 14. So we want opposite over hypotenuse to be x over 14. And then we fill in the blank. The missing side here is going to be the square root of the hypotenuse squared, 196, minus that other side squared, x squared. And now down here, I'll distribute the 98. So theta, we go back to our original substitution. Theta is the inverse sine of the other side. So that's going to be inverse sine of x divided by 14. and then minus 98 times sine of theta times cosine of theta. Sine of theta, we just said, is x over 14. Cosine of theta is adjacent over hypotenuse. So that will give us square root of 196 minus x squared, all divided by the hypotenuse, 14, plus c. And the only thing we have to do left is simplify. This is going to be 98 over 196, which is 1/2. So our final answer, one half, you can put the 1/2 in front, you can put the division by 2 in the bottom, doesn't matter, it's all the same. We believe in algebra. So that'll be our answer. Trig sub. Trig sub's always an interesting one to grade on these exams. I'll appreciate it. Just do it right. Make my life easier. Trying to find mistakes in trig sub is such a pain. Okay. Any parts of that? Any of the concepts there? Everyone understand how we get to our purple triangle? Our Ouija triangle? Take us back and forth between these two different spaces. All right, trig sub here. Trig sub here. Let's do this one, because this one's... So, once again, we see a difference of squares. Difference of squares. First thing we say to ourselves is not tangent. And then we have to figure out if it's sine or secant. And so here it's going to be, the question is, which one is an identity, secant squared minus 1 or sine squared minus 1? Sine squared minus 1 would be negative cosine squared, not good, so it's secant. Because secant squared minus 1, if we look at our triangle, secant squared minus 1 is tan squared. So it'll be a secant. Okay, first though, I would like it to be a difference of squares with a trailing 1. So that 400 is going to factor out. It's in the denominator, so it's going to come out in the denominator, and it has to come out with that same power that's on it, on the expression that it's in, 3/2. And as we've seen many times, that other term doesn't have a 400. Doesn't matter, we just create one. And so it's going to end up being x squared over 400, which we'll combine, we'll move it in 1 second. We'll put it as a single square in one moment. And a lot of times you get good at just doing that in one step, but okay, so here on the outside, the 2 is in the denominator, so that's a root. So that's the square root of 400. The square root of 400 is 20, and then we have 20 cubed. We'll just write it as 20 cubed for a moment. And then in here we have dx over, let's turn this into a single square, so that's x divided by 20, quantity squared, minus 1, all that's raised to the 3/2 power. All right, so now we have a difference of squares with a trailing 1. We use secant. So x divided by 20 is going to be secant of theta. We differentiate both sides. We get 1/20 dx. The derivative of secant is sectan. Now we're ready to convert all the x's over to thetas. We're ready. We're willing, we're able, we're competent. So, in the numerator, there's a dx. We come and look down here. If we multiply both sides by 20, we've got dx isolated if we multiply by 20. So dx is going to be 20 sectan times d theta. So 20 sectan d theta. And then down under, we've got secant squared minus 1 raised to the 3/2 power. One of the 20s cancels for sure. So we are left with 1 over 20 squared, which is 1/400. All right, in the denominator, let's do a little finagling. The numerator, we're just going to leave it alone for a moment. Sectan. Down below, secant squared minus 1. Again, we look at our triangle. Hypotenuse squared minus 1 is going to be that side squared, so tan squared. So we have tangent squared of theta raised to the 3/2 power. Power to power, what's the exponential rule, exponent rule of power to power? Multiply. Power to power, we multiply. So this is going to turn into 1 over 400 integral sectan in the numerator. In the denominator, we're going to end up with tan cubed. So one of those tangents is going to cancel, and we're going to be left with secant to the 1 power. So secant to the 1. That's not one of our special cases. So we end up with that. So it does not fit one of our special cases. Secant to an even power, tangent to an odd power. It does not fit. So if it does not fit, you have a couple of choices. Depends on where the square is, really. You could use a Pythagorean identity, but using a Pythagorean identity here, tan squared, sec squared minus 1, you're going to turn the denominator into 2 terms, which is generally bad. We like having the denominator be 1 term because it could distribute if we needed it to. The other option is turn everything to sines and cosines. Right? So let's do that. So convert to sines and cosines. So in the numerator, we're going to have 1 over cosine. That's not right, I like that. So 1 over cosine. Actually, I'm going to multiply by the reciprocal of the denominator, so let's just do it like this. So 1 over cosine, that's secant. And then tan squared is sine squared over cosine squared, but we're dividing by it, so we're going to flip it. So it's going to be cosine squared over sine squared. So we have that. One of the cosines will cancel, and we'll be ready to rumble. What will we let u equal? Sine. Because in the numerator, there's cosine theta d theta. So if you let u be sine, the derivative of sine is cosine. So that's going to work perfectly. So u will be sine of theta. du will be cosine of theta d theta. And this integral then becomes u to the negative 2 du. Beauty. Wow. So we can power rule it. We have 1/400th. We add 1 to the exponent and get -1. And then we divide by the new exponent. So we're going to have -1 over u plus c. Then we go back to sine. So we're going to have -1/400th times, let's see, u is sine, so 1 over sine, which we could turn to cosecant if we wanted, but we don't need to, plus c. Purple triangle coming our way. We've got to get from theta back to x. So we draw our purple triangle, quadrant 1, theta in the corner as if it's living in quadrant 1. And then we fill in 2 sides based on our substitution up here. Secant is x over 20. Secant is hypotenuse over adjacent. It's the reciprocal of cosine. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So hypotenuse over adjacent. Secant of theta is x over 20. And then we have to get our missing side. Square root hypotenuse squared minus other side squared. Now we can finish this off. So sine of theta, opposite over hypotenuse, but then we're flipping it. So hypotenuse over opposite. So x divided by square root x squared minus 400 plus c. Okay, good.
Good now.
46 hours, hopefully you're good. I feel like colors help. Do you think colors help?
Yeah.
We went to North Carolina a couple weeks ago and went to UNC Chapel Hill. It's like all chalkboards. I'm like, man, that makes life so much harder, I feel like.
Maybe chalk.
Chalk.
Where did we get the x squared minus 400 from?
So the x squared, this here,
Yeah.
so it came from the missing side, which was from Pythagorean theorem. Secant is hypotenuse over adjacent. And then this missing side is the square root of the hypotenuse squared minus that leg squared. So Pythagorean theorem on the purple triangle. Other questions on it? Makes sense. Okay. We'll pass this next trig sub. It's the tangent one. It's the easier one. You can look at the video. Let's do one PFD, and then I want to do some improper integration. PFD is pretty routine because it's so formulaic. Let's do that one. That encompasses both. And then we'll do the improper integration, which is much more conceptual. So PFD, if your denominator factors, that's when you think about using PFD. And when you factor your denominator, you have to completely factor it into linear and irreducible quadratic factors. This sum of squares here is irreducible. You would need imaginary numbers in order to set that to 0 and solve for x. You'd have to have imaginaries, so we don't want that. So irreducible quadratics or linears. So the inside here, the integrand, we are going to rewrite this as two fractions. A fraction that has x in the denominator and a fraction that has x squared plus 25 in the denominator. So those are your partial fractions. And in the numerator for an irreducible quadratic, you need a linear. So we want the numerator to be the most general numerator possible that keeps this as a proper fraction. So if the denominator is a quadratic, we want the numerator to be a linear. And then we multiply both sides by the left's denominator. And on this side, let's see, we get the x multiplied by bx plus c. We'll have that. So that's our PFD equation. And with an irreducible quadratic in there, it's using the convenient value method, there's one convenient value of 0. So we could try to do a hybrid method. Let's just go the traditional method this time all the way through. So we'll distribute everything and then we'll match coefficients. So on the left side, I'm going to think of there being a placeholder of 0x squared in the x squared position. So now we just match coefficients. Coefficient of x squared, coefficient of x squared, coefficient of x squared. This is going to give us a system. We'll have 0 equals a plus b. And then we're going to go to coefficient of x, which is 1. Over here, oh, there's only one coefficient of x over there. So it looks like 1 is going to equal c. And then the constant on the left is a 1. The constant on the right, we just have that, 25a. So this bottom row tells us that a is 1 over 25. The top row then tells us that b is negative 1 over 25. So we have the whole PFD solved for. I'm going to call the integral omega just to refer to it. I don't want to write all the way up there. So omega will equal the integral of a divided by x. So 1/25 over x plus b, which is minus 1/25, times x plus c over x squared plus 25. All right, so that is where we're at. We're going to split some fractions. So here, I'm going to split this like that. So I'm going to take the x squared plus 25 and divide it into the x, and then split it the other way also. So go that way also. So the x squared over 25 is going to go into both terms in the numerator. The green is going to be what kind of integral? Log, because the derivative of the denominator is 2x, which is a multiple of the numerator. How about the pink one? What will that be? Arctan, a 1 over x squared plus 25. Okay, so this first one is a log. So we have 1/25 natural log of absolute x. That's that one. And then let's write this out. So the green here, if we factor out the 1/25 from the numerator, the negative 1/25, we'll be left with x over x squared plus 25 dx for that piece. And the last piece, we'll distribute the integral over here. We'll have plus integral 1 over x squared plus 25. So that gives us, we've got that first term already completed. The middle one here, the denominator's derivative is 2x. So I'm going to put a 2 up in the top. But if we put a 2 in the top, we have to put a 2 in the denominator. So that will be minus 1/50th natural log absolute value of the denominator. The denominator is always positive, though, so we don't have to put in the absolute value bars. And then with this one, we are going to, I'm just going to rewrite this one here for a second. If I factor out the 25, we're going to have 1 over x divided by 5 quantity squared plus 1. So when we integrate it, we'll have 1/25th arctangent of x over 5 plus c, and then in this little RCR gap, what's going to go in the RCR gap?
5.
So we're going to divide by 1/5, which will be multiplication by 5. So 5 will go in here. And then the only simplification is 5 into 5 once, 5 into 25, 5 times. And that will be our answer. So remember this fraction splitting thing. 90% of the time when we fraction split, it's one denominator term that's splitting into the numerator. But you can also fraction split with a two-term, with a binomial, and put the binomial into each also. All right, let's take a look at improper integration. So that's a super conceptual thing. So let's make sure we can hammer through some improper integration. And maybe some of these we'll see. We'll at least set all the impropers up because these are more important to get details down. So the first type of improper integral is the type where we have a horizontally unbounded region. So we're, again, unbounded means that the area, the region, you can't put a circle around it because it goes off forever. But we don't know that that area is infinite. That area could be finite, which is what's weird. So here, with this type, we instantly see that it's improper. And the very next thing we have to do, which a couple of you didn't do on your worksheet, is write limit. So it has to be a limit. You need to have a limit for the notation to be right. You don't just want to leave infinity in that limit of integration. You've got to pull the infinity out and put a letter in. And then power rule, so we're going to write this as x to the negative 1/2. So then we get limit, we add 1 to the exponent, we divide by the new exponent. And if you want to pull the 2 out to the front, you can. Does not matter either way. This will be the square root of b minus the square root of 11. And this limit is as b goes all the way to infinity. And what is that limit? Does that limit exist? No, that limit does not exist because b, the square root of b as b goes to infinity is going to infinity. Infinity minus a constant is still infinity. So it's best to say that this limit is infinity. It's true that DNE that's correct, but it's better, you want to be as precise as you possibly can. This is a little more precise than just saying D and E. It's true that it doesn't exist. And does this match what we talked about in the worksheet with our threshold of x in the denominator?
Yes.
Right? So we saw that 1 over x had infinite area. And if the power on x is less than 1, that tail along the x-axis is even further away from the x-axis. So it's got to be infinite also. What we saw is for the horizontal tail to be finite, the power on x had to be bigger than 1. So less than 1, the horizontal tail is going to be infinite. All right. All right, here's one of those ones where we know that if it was just 9 over x, we know it would be infinite, it'd diverge. But this little natural log of x thing, that function goes to infinity. And our sort of reasoning, we know if it was x times x, it would definitely converge. This is in between. So x ln x is going to be in between x and x squared. So it's not obvious whether this is going to be, we can't just apply our threshold concept here. But first thing we write down, limit as b goes to infinity. First thing we write down. Integral from 2 to b. So we're there. So that's always the first step with an improper integral. And with these horizontally unbounded ones, it should be jumping right out at you that it's improper because you have an infinite limit. Limit of integration can't be infinity. So what technique will we use here? It is not log form, so it's log form if the denominator's derivative is the numerator.
But it is.
The derivative of this denominator is 9?
No, the derivative of ln of x is 1 over x.
Yes. So that's not log form, though. That's u substitution with u being log of x.
Okay.
So log form is when the denominator's derivative matches the numerator. U substitution works perfectly here because if we let u be log of x, its derivative is there. So it's not log form, but we use log. So yeah, there's definitely, they're connected. Right, but you're 100% right that if we do u substitution with that, whatever we choose for u, if its derivative is present, that's going to make the u substitution work. So that's going to work really quite nice here. And that 9, we could factor it all the way to the front. I might as well do that. Constants can just slip to the front. So inside the integral, the u is in the denominator, and then dx over x, that's all going to be du. So we're going to have 1 over u du. And we're not going to convert to u limits. We'll just use placeholder limits. So we get that. Does that look good to everyone? Landon? Okay. And what's the integral of 1 over u? Integral of 1 over u, natural log, absolute value of u. Okay, good. Absolute value of u. And we don't have limits yet. We're just sort of biding our time. Now we back substitute. And we get limit of natural log of absolute value of natural log of x. And we go back to our x limits 2 to b. So we got log of log. Log of a log. So we'll have 9 limit. And the limit is as b goes to infinity. So we'll put that back since we're about to apply it. So we're going to have log. And b is positive. We see that we're going from 2 to infinity, so we don't need absolutes anymore. So it's going to be log of b minus log of 2. And what is that limit? Infinity. Because log, so if we look in here, log of b, this part goes to infinity. Log of b looks like this, it's going to infinity. And so you have the inside of this outer log is going to infinity, so it must also be going to infinity. Right? The inside here, inside there is going to infinity, so this log is going to infinity. And then this is now the inside of the outer log. If the inside of that's going to infinity, that function's also going to infinity. So that is going to infinity. This is going to infinity. And if you subtract off a tiny constant, that doesn't change anything. If you multiply by 9, that doesn't change anything. So we are going to get that area is infinite. You could say that the integral diverges. So we say that it diverges. All right. Cool. Crazy logs. All right, so here's one of the hidden improper integrals. We don't see infinity like ringing a bell in our face. But what we notice is that if you plugged in 7 for the x, you would get division by 0. So that tells us it's not a definite integral. It looks like a definite integral, but it's in disguise. It's actually an improper integral. And so we need to have a limit right away. So we're going to approach 7. And do we approach 7 from the left or from the right?
From the right.
So if we think about our interval, we've got our interval. We're going from 7, 8. And if we're going to be approaching 7, we want to stay within our domain. So we're inside here. As we start moving towards 7, we are coming in from the right-hand side. So that will be a limit as c approaches 7 from the right. Well, this integral is not too bad. Because if we pop this factor up to the numerator, we can just use power rule. It's just a power rule problem. So we'll have limit. We add 1 to the exponent, so we're going to add 4/4. So we'll end up with -1/4. And then we have to divide by the new exponent. So dividing by -1/4. It's the same thing as multiplying by -4. So I'm going to squeeze in a multiplication of -4 in front. Now, typically, we would have to do an RCR also. But what is the derivative of this base? 1. So dividing by 1 is not very, you can't see it. It's happening, you just don't see it. And then our limits of integration are c to 8. So we'll factor the -4 out to the front. The limit, we'll put in our subscript for the limit. C is going to 7 from the right. When we plug in 8, 8 minus 7 is 1. 1 to any power is 1. Minus, plugging in the c, we're going to have c minus 7 to the -1/4 power. And I'm going to rewrite it one more time just because evaluating limits with negative exponents can be problematic. So it's often easier to see the limit if you write it with positive exponents. So we have that. Okay. So c is going to 7 from the right. Do you see that c minus 7 is then always positive? Right, because we're coming in from the right, so 7.1, 7.01, 7.001. This will always be positive. It's going to 0, but it's going to 0 through positive numbers. So that makes this whole part here, if we are to the right of the minus sign, this whole part that is going to go to positive infinity. So that's why the one-sided limit's important, because if you had a two-sided limit, you couldn't say this. If you were coming into 7, say through 6.9, 6.99, this would always be negative. And then the fourth root of a negative wouldn't work anyway, but the point is, if you're coming from the right, this is going to go to infinity. Denominator is going to 0 through positive values. And then 1 minus infinity would be negative infinity, right? And then if you multiply this negative infinity quantity times -4, you will get positive infinity. And so then let's ask ourselves whether this tracks with our threshold idea. So this is a vertical tail. So vertical tail, and this power on x, if you forget about the shifting of -7, the power on x is bigger than 1. So if it was horizontal, you would get finite, but because it's vertical, you will get infinite. So the power on x is bigger than 1, and if you were doing 1 to infinity, you would get a finite answer because the power on x is bigger than 1. But for the vertical tail, the power on x to be finite would have to be less than 1. Okay, so that's why it's infinite. All right, one more improper. Actually, let's pass on this one. You can watch the video on this. This one's a pretty straightforward volume one. We did one today even. So let's do at least one of these differential equation ones. Let's see. Let's do the second one. At least do one of these. So with the differential equations, this is the easiest type of differential equation because the derivative piece of it's isolated. And so the strategy is to integrate twice. So if we want to find the function that satisfies this differential equation, we do it in steps. So y prime is going to be found by integrating the right-hand side. So what we are essentially doing is integrating both sides of the equation. And the integral of the left side of the equation, if you integrate y double prime, you get to y prime. So this is going to be our first step. I want to do that. And now we just use our power rule. So we're going to have x to the 12 over 12. And then here we're going to have x to the 4 over 4. Here we're going to have x to the 2 over 2. Here we're going to have x to the -4 divided by -4. And then our first constant of integration. We kind of know from experience by this point that if you have a second order ODE, when you get your solution, you're going to have two constants. If you had a third order, so third derivative, you'd end up with three constants. One derivative, one constant. So we're there. Now to get to y, we integrate y prime. So now we're just going to integrate this whole thing to get to y prime. So we just integrate that with respect to x. And that's going to get us to y. So we have a little bit of simplification we can do here too. Let's see. That's 6, and that's 35. That's 39. 60, 78. And then 3 goes into there twice. 3 goes into there 13 times. So we'll do a little simplification as we go. Oh, look at that. So this is going to be x to the 13 over 13. And so the 13s will cancel x to the 13 over 13. The over 13 will cancel. So we'll get 1/2 x to the 13th plus this one, we're going to have a 5 and a 2. And when we integrate, we're going to get x to the 5 over 5. The 5s will cancel, so we'll get 1/2 x to the 5th. Minus, here we'll get x to the 3 over 3. So we're going to get 1/2 multiplied by x to the 3. Here we have -9. So -9. We add 1 to the exponent, we get x to the -3. We're going to divide by -3. Let's put it like this. And then plus c1x plus c2. So that's our antiderivative. The only thing we can do is simplify this stuff in here. This will turn into a +3. And that'll be our solution. So that function is the solution to that differential equation. Okay, so we'll stop there. The ones that we didn't get to, there's videos for all of them, so if you're confused on any of them, watch the video, shoot me an email, all that stuff, and study hard. I'll see you on Thursday, and then we'll have spring break. Well, how about that? Perfect timing, test, and then you get to relax for a week. Although we are going to be entering the hardest unit, so maybe you should not just completely relax during spring break. Maybe you should read a little bit about infinite series. But
Will we get our test scores after spring break?
yeah. Oh yeah. I'm going to Steamboat. I'm going to Steamboat. Yeah, I don't know when I'll grade them. It depends on.
Just at some point.
You'll get them the day you come back for sure. They'll be graded by then for sure.
With the laptop next to you.
Right.
Going through it.
Sitting at Strawberry, grading on my phone.
So the final replaces your lowest test grade, right?
Yes.
Even if it's a 0?
Yes. Why are you asking that question?
I'm joking.